so we're using that same bearing. Is it the same bearing from that previous one? Maybe I should have just continued. Yeah. So this is the continuation from this problem right here. We're saying, and I should have made just a single video out of it, and it's probably the reason why I had made a video with this one right here. So anyway, so this is like problem 1139 from at least the 9th or 10th edition. And so in the previous video, we did a pretty simple example. And I was like, well, why did I do that example again? I think it's because it's a setup for this one right here. So watch that other video to see how we got this. But now we're going to continue on. And there was actually missing information here where we had 2,000 RPM. Let's see, so we have that same bearing from that problem is to be subjected to two-step loading of 4 minutes with 18 kilonewtons and then 6 minutes with 30 kilonewtons, right? And so it's going to go on, off. And both are applied when the machine is operating at 2,000 RPM. This is something that we needed to know that was not even wasn't in the 5th edition. So this cycle is to be repeated until failure, and we want to estimate the life in revolutions, hours, and loading cycle. So we could actually solve this, I think, in terms of loading cycles. Let's double check. I seem to recall you couldn't do it in hours unless you knew what the RPM was, which was kind of a weird thing for how they had asked it. All right, so it's just a little bit more complicated here. So from the previous problem right here, so some of the previous information that we were going to have right here is that we had this L1 at at 18 kilonewtons, we got this right here, right? Yep, 18. And then at 30, we got this number, right? And notice that this one, 18, was more than, or 18 was lower than what was in the catalog, but 30 was higher than what was in the catalog, right? So we had like something that was above 1 million and something that was below 1 million. So that was a good observation that I should have pointed out. But now we're going to have like this turn fraction idea that's added into the complication here. So let me write down what those numbers were. And L2 was 3.098 E5 revs, right? And so the concept here is if little L1 over big L1 plus little L2 over big L2 is equal to 1. Then, so if that's true, then damage fraction 1 times L plus damage fraction 2 times L is equal to 1, right? All right, so if so now what we could do is we could figure out what that little L is going to be. We could figure out the life, right? So if it goes 6 minutes and 4 minutes right here, we could figure out that the damage fraction 1, or the turn fraction, is just going to be 4 minutes over 10 minutes, right? And the damage fraction 2 is just going to be 6 minutes over 10 minutes, 0.6. So we could put this back up into here, and we could say that the life right here is going to be 1 over, okay, I did a little bit of manipulation here. I took out this as the common denominator, yes. So I have F1 over L1 plus F2 over L2 right here, or 1 over 0.4 divided by 1434 E6 plus 0.6 over 3.098 E5. So our life, our predicted life, is 451,600 revs, which seems to me just to be a little bit too many sig figs, right? But we're going to use this, I think, down below, right? So we want to try to figure, so that's the number of revolutions. They've asked for the number of revolutions, and we didn't need the RPM. But if we want the hours, now we have to do a little bit more work here. So we could say that we could have the number, we'll call a cycle, right, is 10 minutes, right? So we'll figure out how many how many things we're going to have. So we're going to have, and we also know that it's going to be as situation one, I'll call it situation one, is 4 minutes per cycle. Just a minute here. I'm going to need to pause. I'm going to turn my fan back on because I have the loud speaker talking. Okay. Yeah, it's hard when you're hearing someone's conversation in your ear to try to concentrate. Okay, so like this is going to be at 2,000 RPM. With these are revolutions per minute, right? So we can say that these are going to be 8,000 revolutions per cycle. Right? So we're going to say the cycle is 10 minutes. Occurs every 10 minutes, I should say. I misspelled cycle. 2,000 rev per minute. So we have 12,000 revolutions per cycle. So that means that we have 20,000 revs per cycle. For every 10 minutes, there's this many revolutions right here. So the total cycles is going to be, let me see, I gotta click on my office hours to tell them that I'm still here. Yeah, I'm still here. What we're going to say is we have 451,600 revolutions. We're going to say, well, how many cycles is that going to be? That is 451,600 revs divided by 20,000, I should say, revs per cycle. So what we decide is we have 22.58 cycles, which means, and we said we had 10 minutes per cycle. Why can't I spell cycle today? Cycle. This looks wrong. That comes out to 225.8 minutes, which is 3.76 hours. If you go, I mean, this looks like really straightforward and simple, but like it'd be interesting, and I might do it in class just to tell you, just solve this. There you go. All right, here you go. Here's the thing for you to do. Think your way through here and solve it. Like say, number of revolutions, hours, and loading cycles, and it'll perplex you, right? It'll be kind of like, wait a minute, how am I supposed to do that? Well, you could once you start to run through the logic of the thing right here, it's like, okay, well, I can see, well, here's the fraction of a time and a fraction of a time. It's really just a test of logic in one way, or it's like a word problem where it's sort of like a little riddle, and you're trying to like work out and think that some kind of rational. Sometimes I refer to this as like you're trying to look for a basis to try to make a judgment. It was like, okay, well, I'm going to weight things based on this. I'll weight it by the percentage of time. So we'll call that the fractional turn, the turn fraction, like 4 out of every 10 minutes and 6 out of every 10 minutes. So we have 40% of the time, 60% of the time, and they could say, well, okay, well then here's numbers. Here's a number of revolutions per minute. So I can figure out revolutions per cycle, and then I can figure out the total number of cycles that this thing would have to do through here, and so I can figure out the amount of time that it would have to put through there. And so it's obvious after you take a look at the thing. So that's kind of an interesting type of thing that you have to do when you have to try to estimate how much something's going to how long something's going to live.